Take a look around you right now. I mean it, really look. Almost absolutely nothing you see is made of a single pure element. Our world isn't neat and isolated. It's a messy, tangled web of materials that are clumped, swirling, and fused together. So how do we make sense of it all? And maybe more importantly, how do we take that chaos and separate it into something pure and useful? Basically, how do you unmix a complex world?
Well, to answer that, we gotta start with the basics: mixtures. A mixture is simply a substance made up of two or more elements physically thrown together. But here is the crucial part: they are not chemically bound. Because they aren't permanently locked together by chemistry, we can actually use their unique physical properties to force them apart. Honestly, much of scientific innovation is literally just the art of unmixing.
Welcome to The Explainer! Today, we're diving deep into the fascinating world of mixtures and how we pull them apart. We're going to take foundational chemistry concepts straight out of the laboratory and see exactly how they apply to everything from the food in our kitchens to life-saving medical devices and even massive global recycling systems.
Here's a quick roadmap for today. We'll kick things off with the messiness of mixtures. Then we'll look at density and heat tricks, move into spinning and clumping, uncover the mystery of colloids, and finally wrap up with science in the real world. Let's get right to it. Section 1. The messiness of mixtures. The absolute basics of mixing and unmixing.
Okay, let's dive into this. Most materials you interact with every day, like a muddy puddle or smoggy air, are non-uniform, heterogeneous mixtures. And because they don't blend perfectly, we can exploit their physical differences to pull them apart. Take a classic piece of lab equipment, the separating funnel. If you pour a mixture of water and mustard oil into it and just let it sit there undisturbed, something super predictable happens. The yellow mustard oil forms a layer right on top, and the water settles completely to the bottom. Why? Simple density. By just opening a little valve at the bottom, we can carefully drain out the heavier water layer, close it right in the nick of time, and boom, we're left with only the lighter mustard oil.
And that brings up two totally vital vocabulary words for us: immiscible versus miscible. Oil and water, they're immiscible liquids. They completely refuse to mix, forming distinct layers, which makes them incredibly easy to separate using just gravity. Miscible liquids, on the other hand, mix uniformly together. Separating those requires some far more complex tricks.
Moving right along to Section 2, density and heat tricks, how we use physical properties to force things apart.
So gravity is a fantastic tool for simple liquids, but when it just isn't enough, especially for solid materials, we have to exploit other basic physical properties, like how a substance reacts to heat. Now, what's really interesting about this concept is a process called sublimation. Imagine you've got a dish filled with crushed camphor and sand. You certainly can't pick the sand out with tweezers, but if you heat that mixture gently, the camphor does a literal magic trick. Upon heating, it changes directly from a solid into a vapor. It entirely skips the liquid phase. The sand? It just sits there, completely unaffected. If we trap that vapor using an inverted glass funnel with a cotton plug at the top, the vapor hits the cooler upper walls and undergoes deposition, turning right back into pure solid white crystals of camphor. Camphor is a really neat laboratory example of a sublimable substance. But I want you to think about your own life for a second. Can you think of an everyday sublimable substance? Where have you seen a solid turn directly into a dramatic, swirling vapor outside of a science class?
If you guessed dry ice, you hit the nail on the head. Dry ice is solid carbon dioxide, and it undergoes this exact same physical trick of sublimation. This is exactly why it's the go-to for ice cream storage and shipping perishables. It stays incredibly cold, and as it warms up, it just turns straight into a gas. No melting, which means absolutely no soggy puddles left behind in your cardboard box. All right, Section 3, spinning and clumping. Time to look at some active separation techniques. Heat and gravity are great passive tools, sure, but sometimes particles are just ridiculously stubborn. When you have a cloudy fluid with particles too tiny for filter paper to catch, you have to get active. And this brilliantly illustrates how we can literally borrow physics from playtime to save lives. Think about a traditional folk dance game like Fugatti or Kikli, where two people lock hands, spin around, and feel that intense outward pull. That is centrifugal force. Now apply that exact same force to a low-cost, hand-powered medical device called a paperfuge, which is mostly just made of cardboard and string. By spinning blood samples at high speeds, zero electricity required, the heavier components of the blood are forced outward and separated. It's an incredibly simple, highly accessible tool that helps detect diseases like malaria in remote off-grid areas. It's a real game changer.
Now, another active technique for those super stubborn, cloudy mixtures is coagulation. Let's say you have incredibly muddy water that just will not settle. What do? First, we toss in a chemical coagulant, like powdered alum. This forces those tiny suspended impurities to suddenly stick to each other and clump up. That's the coagulation part. Then, because those particles have formed into much larger, heavier clumps, gravity finally takes the wheel. They settle right down to the bottom through sedimentation, leaving nice, clear water up top that you can easily pour off.
So, the crucial point here is that coagulation isn't just some heavy-duty industrial water cleaning method. You probably use it right in your own kitchen. Making paneer, or really various types of cheese, relies entirely on this process. By adding an acid like lemon juice or vinegar to warm milk, you are acting as the coagulant. That acid forces the milk proteins to clump together and separate from the watery whey. And just like that, you've got cheese. Moving to section 4, the mystery of colloids. These are basically suspensions in hiding.
Now we are arriving at one of the most fascinating types of mixtures out there. Things like milk or blood usually look totally smooth and uniform to the naked eye, but they are hiding a secret. When you look at the actual particle sizes, it makes perfect sense. In a true solution, like salt water, the dissolved particles are minuscule, less than a single nanometer in diameter. They are never going to settle out. On the flip side, we have suspensions, like sand and water. Their particles are huge, over 1,000 nanometers, so they will absolutely settle to the bottom eventually. But colloids? They sit right in that sweet spot in the middle. The particles are between 1 and 1,000 nanometers. They're small enough that they stay perfectly dispersed without settling, but they're large enough to do something pretty spectacular with light. That spectacular light-messing property? It's called the Tyndall effect, named after the scientist John Tyndall. Because the particles in a colloid or a really fine suspension are just the right size, they physically scatter beams of light. You know that dramatic, epic lighting you see at a nighttime sports stadium? That is the Tyndall effect in action. The light scatters off dust and smoke particles in the air, suddenly making the entire path of those giant floodlights visible. If the air were a perfectly pure solution, the beam itself would literally be invisible from the side. Let's move on and see how this all builds up. Section 5, Science in the Real World. Separation at a massive scale. All the lab tricks we've been talking about today, the funnels, the sublimation, the spinning, the clumping, they aren't just academic exercises for a chemistry textbook. They operate on massive, life-sustaining scales all around us. Right this second, your kidneys are acting as highly advanced filtration systems, constantly separating out and removing waste from your blood. On a larger scale, every single city relies on massive sewage treatment plants to clean wastewater before it goes back into nature, using the exact steps of sedimentation, coagulation, and filtration we just learned. And looking ahead, the recycling industry is facing the ultimate separation challenge. To build a sustainable tech economy, we have to scale up these complex separation techniques to recover valuable raw materials, like lithium, from millions and millions of old dead batteries. Separation is happening everywhere. It's in nature, it's in our cities, and it's inside our own bodies. By improving how we separate waste and recycle materials, we literally hold the tools to make the world cleaner, healthier, and way more sustainable. The basic lab tricks we explored today are the exact mechanisms we need to untangle the environmental messes we've made. So the next time you look at a tangled pile of discarded electronics, or even just a murky river, ask yourself, what clever trick of density, heat, or spinning could unmix this? Because finding the answer to that question, that just might be the key to our entire future.